So, welcome back. In the previous class, I was talking about the sliding mode control for the nonlinear system. So, originally sliding mode control is developed to handle the nonlinear system, because in nature most of the physical system is actually fall in the category of the nonlinear system. In previous class, I was discussing about how to design on-off control for the first order highly uncertain systems. Okay. But originally most of the system is either of second order or higher order. Okay. So, in this lecture I am going to talk about the sliding mode control for the second order nonlinear systems. So, purpose of the discussion and outcomes. So, we are going to demonstrate robustness. I have already discussed that any nonlinear system, we cannot claim that I know the model accurately. There are several uncertainty that is associated with the parameters, as well as we have disturbances from the control channel or through the external sources. So, how basically sliding mode control, and I have already told you that sliding mode control is nothing but some kind of on-off control, and we have to do on-off with very high speed. That is our goal, such that in this lecture we are going to see that how nonlinear systems is converted into linear system after some finite time. Okay. After that, we are also going to talk about insensitivity with respect to some classes of perturbation. What is meaning of insensitivity? Means it means that after finite time system become insensitive. They do not feel any kind of disturbance. Okay. So, that is the meaning. And what is outcome? I have already told you that sliding mode control is very easy to design. So, we are also going to talk about the design aspect. So, let us start the today's lecture with the very simple system, second order system, and this is basically second order uncertain system. So, if you have seen the previous lecture, so at that time I was talking about exactly same system, but here this dynamics is not present and our coordinate system is sigma. So, sigma dot h sigma, g sigma and u, and again we are going to assume exactly in the same way that h and g, that is unknown, but we have some kind of assumption associated with h and g. Then only I can able to design the control action, on-off control action. And here this assumption is required. What is physical interpretation of this assumption? We are assuming that control matrix here, since why I am telling matrix, it might possible in this class I am talking about second order system, but in next class I am going to talk about multi input multi output system. At that time this become somehow matrix. So, control we are going to apply through this matrix. So, I am assuming that this is not going to change the sign. So, how to ensure that? You can see that I am always assuming that Gx is bounded by G0, and objective is exactly same like the previous class. Now, we have to design a state feedback control. It means that I am assuming that I know x1 and x2, and then by designing control action u based on the on-off with high switching frequency, I have to make sure that x1 and x2 both tending towards 0 as t tending towards the infinity. Okay. So, here you can see that I have relaxed the assumption. In previous class I am trying to force the trajectory of first order system in finite time, but here I am talking about asymptotic behavior after very large time. Okay. And what basically we are going to do, we are going to design control action such that system's motion is actually converge to pre-selected manifold. Manifold means some kind of lower dimensional space. So in 2-dimensional space I am going to create 1-dimension space, because just I have one control action. Okay, and what I am going to do now, I am going to make sure that sigma equal to 0 in finite time. So here I have taken this choice, but you can able to take any non-linear combination of x1 and x2, that is also possible. I will also justify why I am claiming C1 is greater than 0. So same like the linear case, whenever first I have discussed on off control in first module, and after that what we have done, whenever we have second order system, we are defining the linear combination, and after that we are transforming the system with help of that linear combination. So similarly I am going to do here. So here you can see that this manifold sigma t is C1 x1 plus x2. You can easily able to plot for sigma greater than 0. So this is x1 and this is x2, then this is the line that is going to represent sigma x1 plus x2 equal to 0. So this is nothing but the sigma t, that is lower dimensional space sliding manifold, and what is our job? I have infinite time I have to converge here, and asymptotically or exponentially I am willing to converge to the equilibrium point. By designing on off control with high switching frequency, basically we are trying to maintain along this surface, that is our objective. So here I have x1 dot equal to x2. So and I have already defined x2 plus c x1 equal to sigma. So due to that reason I remove x2, and in place of x2 I have done this kind of substitution. After that I am going to take the derivative of sigma t. So here you can see that I am going to use Newton's philosophy. What Newton is suggesting, suppose that if you want to control some quantity, just control their rate of change, and due to that reason I am going to calculate the rate of change. Here I have calculated the rate of change, I have substituted x1 and x2 dot from the dynamics, and then now by designing this control action I am going to maintain sigma t equal to 0 in finite time. Please see carefully, here I am maintaining sigma equal to 0 in finite time. Okay, if you see the second subsystem, that is exactly equivalent to the previous system like previous class, but here I have just one extra term. Okay, so now what I am going to do, I am going to assume that these two terms are the part of uncertainty. Okay, and now I am going to assume that the absolute value of this term divided by this term is bounded. Okay, so that kind of assumption comes into picture. So what is observation? Motion on the sigma t should be independent of h and g. So we have to design control such that I can able to force sigma t equal to 0 in finite time, and after that I have to maintain. It means that in finite time I am going to converge here, and after that I am going to maintain exactly along to the sliding surface. Practically you can able to see like this. Okay, so now question is, how can we drive the trajectory to the manifold in finite time and keep it there? So again, if you see this problem carefully, you can see that by using some kind of back stepping, this is method of the back stepping. So what basically we are doing, we are trying to partially decouple this system. Okay, so now without the worrying about x1 dynamics, I can design control action u, and I am force sigma equal to 0, and once sigma equal to 0, then this is actually nothing but the first order system, and using Newton's law now you can able to design again. So you have already learned that in first module that if x1 is 0, then x1 dot should be x1 greater than 0, then x1 dot should be less than 0, and similarly we have to do here, then we will converge to the origin, and due to that reason C1 should be greater than 0. Okay, so and one more important thing I have already told you, that you can able to select any kind of manifold, but here once you will design manifold like this, then your subsystem you can see that looks like minus alpha x1 t. So now you have to design some kind of control mechanism, okay, and some, it might possible some more term comes into picture in the second dynamics, but reduced order dynamics will come like this. So using Lyapunov method you have to stabilize this system. Now we have somehow partially decoupled the system. So I am just going to look into this dynamics, and this dynamics is exactly same like the previous class. So I am going to adopt this similar kind of methodology. What I am going to do? I am going to design some kind of gain that is depending on the state. So this is a state dependent gain, because what is our target? You can start anywhere in two dimensional space, anywhere, and after that I have to converge to the equilibrium point asymptotically. That is our aim. And since this is uncertain, I don't know exact value, and due to that reason I have to actually define some kind of a state dependent gain, and this is beta 0, that is the constant gain, because once you converge very near to the origin, then at that time value of this is very small. So this value will maintain the sliding mode control, okay, that is our main target, okay. And h and g, so in previous class since I have just this term, so now I have these two terms, and due to that reason this kind of inequality comes into picture. So this is our assumption. So this assumption you have to check at each and every time. So now you can see that same like previous class, since I have to stabilize sigma equal to 0 in finite time, so I am going to apply Newton's way of Lyapunov stability, finite time stability. I am going to select same 1 by half sigma square, this is positive definite, and after that v dot, if you do calculation like previous class, and due to that reason I have actually removed that kind of calculation. Now you can see that I will get this kind of inequality, okay. So what is our claim? V dot is less than equal to 0, okay. And in previous class we have already proved that if this kind of dynamics comes into picture, I will do substitution of mod sigma in terms of v, and somehow some term associated with v power half comes into picture, and using comparison lemma I can able to prove that v equal to 0 in some finite t greater than equal to t, okay, and that will maintain. And due to that reason now I am not going to repeat same kind of exercise, please do by yourself. So once sigma equal to 0, now you can see that magic happens, there is no uncertainty in this system, and after that what happens? Now second order system is actually converted into first order differential algebraic system. What is meaning of differential algebraic system? First equation is differential equation and second equation is algebraic equation, okay. So now this is actually fully decoupled, so you can apply Newton's law and maintain C1 greater than 0. By solution also you can able to see that for any initial condition x1 tending towards 0 as t tending towards infinity, and since sigma is already 0, linear combination is 0, C1 is positive, and here x1 is actually tending towards 0, so I can conclude that x2 is also tending towards 0. Since convergence of x1 is exponential, and due to that reason convergence of x2 is also exponential, otherwise they will not maintain that equal to 0, okay. So in this way I can able to achieve sliding mode behavior for any non-linear second order system, okay. So now if you are working with any practical system, you can take that practical system, you can do mathematical modeling, you can check the condition, and after that you can design the control action. Actually most of time what happens that whenever we are applying control, so during application of control actuator bandwidth is fixed, okay, and due to that reason for simplicity purpose what people actually try to establish, they want to use some kind of constant switch gain, okay. So gain of the controller should finite, and if gain is finite or some kind of value that is not depending on state, it is possible to show that I cannot able to steer trajectory from everywhere and then we will converge to the equilibrium point. So suppose this is two-dimensional space. So in two-dimensional space, it means that now I cannot able to start from anywhere and converge to the equilibrium point. Why? Because we don't have sufficient control, and due to that reason we have to estimate this region. Most of time nonlinear system is actually evolving in some kind of limited space, and due to that reason this methodology is completely working in practical situation. So now what I am going to assume, I am assuming that I have simple relay. What is meaning of relay? Some kind of gain and switch, and then I am going to force sigma equal to 0 in finite time. That is our objective. So again you can see that in previous place, if you see the assumption, so how basically when this k become constant, now assumption is going to change. Here this is function of xt, but once you maintain just constant gain, then this become constant. Okay, so now I have to calculate region of attraction. What is meaning of region of attraction? I am able to give guarantee that if I start somewhere in two-dimensional space, then I can able to converge to the equilibrium point. So that kind of guaranteed region I have to select. How to select? So again methodology is very simple. What you can do, you can start with the Lyapunov function, okay, and then you have to maintain sigma dot less than equal to 0. Okay, since k is finite, then you are going to get this kind of criteria. Now what you can do, you can apply this kind of criteria to the reduced order dynamics. Okay, so this is completely not reduced, because here sigma t, once sigma t is exactly become 0, then only I can tell that second order system is converted into first order system, but here this is still a second order system. Okay, in order to find region of attraction, what I am going to do, I will just define Lyapunov function with respect to first variable. I will actually substitute this kind of condition, and using this condition I can able to tell that if you start from this particular ball, then you are able to converge to the equilibrium point. Okay, this set is called positively invariant set. What is meaning of invariant set? Meaning of invariant set is that if you start from that set, you are going to remain forever. You cannot going to leave. What is meaning of positive? So engineering system, we are assuming that only evolve in positive direction. Okay, so here t equal to 0, then this is t2. So we are moving in positive direction, but for mathematician direction is not matter. Time may be negative also. At that time they are just using invariant. Okay, so now you can able to calculate. It means this condition, it means that you can start anywhere in this space. I am going to give you guarantee that you are going to converge to the equilibrium point. Okay, now this is depending on A, and choice of A is fully depend on you. Okay, so this kind of stabilization is called semi-global stabilization. It means that if I enlarge A, then my region of attraction is going to enlarge. Okay, and in this way you can see here that both dynamics x1 and x2 is involved. Why? x1 is less than equal to A by c1, and what is c1? That is the gain of sliding surface. Sigma is nothing but I have x2 plus c1 x1. So in this way we have restriction on x1 and x2, and if you plot it, then you are able to find some kind of ball. Okay, here ball doesn't mean that some kind of spherical things. Ball may be line, point, anything. Okay, that is depending on the situation. Now since in previous problem you have seen that I was talking about semi-global stabilization. Okay, most of time students are very confused with these kind of terminology, and due to that reason what I am going to do here, I am going to tell you that all sort of the stabilization that is particularly people are using in the course of nonlinear control. So from Khalil book you can able to see it. Okay, so up to this time what we have seen, that if I have second order system, then I have two different methodology. I will convert second order system in the framework of the sliding surface using back stepping, and then second order problem is converted into exactly like first order problem. I will solve first order problem, I will apply Newton's law, and then I will able to solve overall problem. So everywhere you can just able to apply some idea of the Lyapunov function as well as some idea of the Newton's. So now in this section I am going to talk about the types of stabilization. So quickly I am going to introduce everything. So suppose I have force system. This system is called force system. Here I am assuming that X belongs to some D, that is subset of the Rn. What does it mean? Because non-linear system, mathematical model of non-linear system is not valid everywhere. So I am assuming that that is only valid in D. Control I cannot able to apply anything. So I am assuming that control will lie in this region, that is subset of M. Okay. Now I am going to design some kind of state feedback control. So most of time you might have actually learned during linear control course that people are suggesting that whenever you have non-linear system, you can linearize it about the operating point and then you can apply the control. So if you will do, and if you will get x t tending towards 0 as t tending towards infinity, so that kind of stabilization is called local stabilization. It means that your control only give you surety that if you start in neighborhood of the equilibrium point, you can able to tend towards 0 as t tending towards infinity. Okay. So now second kind of stabilization is called regional stabilization. Okay. So in regional stabilization, in some way we are somehow first able to understand the physical meaning of the system where mathematical model is valid. Okay. And after that, using Lyapunov way, we are trying to establish some kind of region such that if I start from this region, I will converge to the equilibrium point. Here region is not depending on some kind of parameter. Okay. So regional stabilization means using some kind of Lyapunov way or some kind of other technique, I am going to give guarantee first that if you start anywhere in this space, then you are going to converge to the equilibrium point, and after that we are designing control, asymptotic control accordingly. Okay. So that kind of stabilization is called regional stabilization. What is meaning of global stabilization? So global stabilization is nothing but we are giving guarantee that if you start anywhere from the state space. Okay. In first problem we have already seen that I was talking about global stabilization. Okay. It means that irrespective of our initial condition, I will converge to the equilibrium point. What is meaning of semi-global stabilization? Now this word I have already used, and what you have seen that our region of attraction is function of the parameter. Okay. So sigma is lying between A I can able to decrease or increase. So similarly you can see that whatever control I am going to design, that is depending on the parameter. Okay, some choice of parameter, and if you tend this parameter towards infinity, then you will achieve again global stabilization. Okay. So somehow semi-global control is always depending on the parameter. So what is the difference between global and semi-global? In semi-global stabilization, I am first forming some kind of compact set. What is meaning of compact set? Some kind of set which is closed and bounded. Okay. So sometimes student will confuse between closed and bounded. They are thinking that closeness is bounded, but that is not the case. Bounded means I have some kind of upper bound. Closed means there exists some kind of sequence such that you will converge to the equilibrium point. Okay. So if you have confusion, please actually go through the real analysis book. You can easily able to understand. Okay. Now what I am going to do, I have taken this non-linear force system x squared, due to x squared this system is non-linear. Now I am going to linearize this system. So if you linearize this system, then I have just x dot equal to u. So just you can reject the non-linear term. Now I will design control like this. So you can see that if system like this, then I can able to talk about global stabilization. But if you substitute this control, due to this term, I cannot able to achieve the global stabilization. So at that time I am going to talk about regional stabilization. Okay. Using Lyapunov way, you can able to confirm that this is the region of attraction. Okay. And how regional stabilization and semi-global stabilization is different, I have already told you that in semi-global stabilization, our control is depending on the some kind of parameter, and parameter I can able to increase and decrease. and based on that I can able to achieve the semi-global stabilization. In the previous problem, you can see that I can able to design some kind of control kx minus x square, and then our system is fully linear, okay, and you can able to get global stabilization. But now you can see that control magnitude is very high. If your initial condition is high, then x square, you can see that control is very high. So most of time this is the practical situation. So in practical situation what happens, we are talking about practical stabilization, okay. So most of time you can see here this term is always bounded by some kind of variable, that is delta, okay, and this is not equal to 0 at origin, and due to that reason origin is no longer a equilibrium point. So at that time basically we are not hoping some kind of uniform asymptotic stability. Why uniform? Because this dynamics is depending on time, so we have to give guarantee that for all time this result will true. So due to that reason uniform term comes into picture, okay. Now in this particular situation, when equilibrium point or origin is not a equilibrium point, at that time we are talking about uniform or ultimate bond, okay. It means that I want to maintain trajectory around the equilibrium point, okay, and ultimate or uniform bond concept I have already discussed during the first lecture, okay. So what basically we are going to do now, we are going to design control such that our futuristic trajectory will lie in this region for all finite time. So you have to calculate the finite time, and after that you have to maintain it, okay. So if locally you can able to maintain, then this is practical stabilization, and where control gain is not depending on parameter. If control gain is also depending on parameter, at that time we are going to use some kind of term, that is semi-global kind of terminology we are going to use, okay. So let us see it. So I have taken this system, I have designed this kind of control action. Now I will select nonlinear system. Most of time if you have nonlinear system, so it is good to treat using the Lyapunov function, okay. And V dot I am going to calculate. Here you can see that this term is actually negative, all other terms are positive. So I am going to divide this term into three parts, k by 3, k by 3, k by 3, and after that this part is going to maintain the convergence. Another part is going to take care about, one term is going to takes care about x cube, another one is x and d, okay. And then it is very easy to check that you can able to maintain this, okay. So if you select k greater than equal to 3 delta by epsilon, and k you can select very large, then you will get semi-global practical stabilization. Why semi-global? Because now by selecting gain k, very large gain k, you can able to cover more region, okay. Now how to achieve global practical stabilization? So in global practical stabilization I am telling that you can start anywhere, okay. So if your gain is tending towards infinity, then I can able to select any value, okay. So in semi-global, just semi-global stabilization, it might possible even if gain tending towards infinity, I cannot able to cover whole region. But here in global practical stabilization, I can able to cover all region, and trajectory is going to maintain about the equilibrium point. So this is very easy calculation. You can apply this control, you can design this Lyapunov function and maintain this kind of stability. Please check by yourself. Now I have taken one pendulum system. So this is very practical system. Several problem is actually driven by this practical system, okay. So this is second order system, okay, and I have just designed here the relay based control. What is meaning of relay? Gain is constant, sliding surface a1 x1 plus x2. So in place of c1 I have just written a1. You can apply this kind of parameter and please do simulation. So after doing simulation you can able to see the response like this. So MATLAB code I am also going to provide during the tutorial session. I am also going to give the MATLAB code. So you can define the initial condition. So this is the time of a span, means up to what time you are willing to do simulation. After that you can apply OD45 and then you can define x1 and x2, and then dynamics part you can define. This will give the plotting command, and after that you can define the dynamics and then you can simulate it, okay, and you will get this kind of result. Okay. So, here theta is actually going to converge to some value theta, the theta difference, that is 1.05. Okay, and sliding surface you can see that is converging towards the equilibrium point. So, now it is time to conclude this lecture. So, we have discussed the sliding mode control for second order system. We have also established the semi global stabilization. Okay, and after that we try to understand different kind of notion which is actually used in the nonlinear control courses. Okay, and this notion is very practical. Okay, and I again tell you, for higher order system please try to understand these notions carefully. So, thank you very much.